In this video, we introduce ReCoDe, a method for learning dynamic constraints to improve coordination in multi-agent systems. Constraints are a powerful mechanism for shaping the behavior of multi-agent systems. They can guide agents, prevent entry into unsafe regions, enforce formations, and avoid collisions. For instance, roads constrain movement in a way that both facilitates navigation and reduces the likelihood of collisions. In addition to physical constraints, virtual constraints, such as traffic rules, help structure agent behavior. These rules enable agents to resolve conflicts, prevent accidents, and achieve coordinated motion, particularly in dense environments. In robotics, constrained optimization provides a principled framework for controller design, particularly in single-agent systems. However, in multi-agent scenarios, it remains unclear what forms of constraints are most effective for enabling coordination. How can agents learn to avoid deadlocks, yield to one another, or reach consensus on joint actions? We propose addressing this challenge by learning such constraints directly. ReCoDe begins with a pre-existing expert controller that may be suboptimal in coordination-heavy tasks. Using multi-agent reinforcement learning, agents learn additional constraints that augment the base controller. Rather than directly interacting with the environment, agents engage in structured communication to jointly design constraints in real time. This approach retains the strengths of the expert controller while compensating for its limitations in collaborative settings. This example demonstrates ReCoDe in the connectivity scenario, where agents must move from the bottom to the top of a corridor while never disconnecting any communication link and avoiding collisions. The expert controller fails to complete the task, frequently resulting in deadlocks. With ReCoDe's learnt constraints, however, agents coordinate effectively and complete the task successfully. In the waypoint scenario, agents must reach same-colored goal locations within a confined space. The expert controller performs well for most of the episode but fails due to a deadlock at the final stage. ReCoDe leverages the expert's strengths while adapting its behavior at critical moments to ensure task completion. In this real-world scenario, two teams of ground robots must switch positions in a narrow corridor, with only partial observability and local communication. The handcrafted controller consistently results in deadlock. In contrast, with ReCoDe, all 6 robots learn to yield and coordinate, achieving successful task execution despite real-world uncertainties such as tracking noise, communication delays, and actuation errors. In evaluation, we find that ReCoDe outperforms state-of-the-art learning-based, non-learning, and hybrid methods across a range of coordination tasks. Moreover, it is highly sample-efficient, requiring only 5% as many training samples as end-to-end multi-agent reinforcement learning to converge. Additional results and scenarios are presented in the paper. Thank you for your interest in our work.